Good morning, Precalc. I hope everybody's doing okay. We are starting chapter 3. This is exponents and logs. Should have done this in Algebra 2, but we're going to build on that and do some crazy things like something called Newton's Law of Cooling and all kinds of fun. So today should be review. An exponential function is anything that can be written, where's my cursor? In this form right down here. We're going to put that on the next slide. But I had to include this slide because it says, in this chapter, we will explore exponential and logarithmic functions. These are considered to be transcendental functions because they cannot be expressed in terms of algebraic operations. In effect, they transcend algebra. It sounds like we're so smart. We are studying transcendental functions. All right, we are so smart. So anything that can be written as f of x equals a times b to the x. Now, b has to be positive, okay? Oh, I'm sorry. If b is greater than 1, it is an exponential growth function. If it's between 0 and 1, it's a decay function. It does have to be positive, the b value. The a value can't be 0, okay? B can't be 1 because 1 to any power would just be 1, and that would be linear. Okay, actually, yeah, constant function. All right, this is what an exponential growth equation is going to look like when B is greater than 1. You don't have this in your notes, but we're going to graph some of these in a second. It is continually growing, okay? It is increasing the whole time, and it has a horizontal domain at the x-axis, which is the equation y equals 0. Domain. Horizontal asymptote. Let me try that again. It's too early for me. All right. The left end behavior approaches 0, and it does not stop. It will look like it stops on your calculator sometimes, and then the right end behavior is going up. Exponential decay, on the other hand, is reflected across the y-axis kind of here. See how it's flipped going this way? It's not an actual reflection, it's a different b value. So, but if they were related, like 2 to the x, and remember 2 to the negative 1 is 1/2. So if you had 1/2 to the x, it is the reflection across the y-axis of 2 to the x. All right, anyway, it is constantly decreasing. The right end behavior approaches 0, left end behavior approaches infinity, etc. Let's do a little practice here. Oh, here's our favorite one, y equals 2 to the x. So I'm going to put here a times b to the x. All right. And we're going to just do some ordered pairs real quick. 2 to the 0 power. Whoops, let me, sorry, my brain is not quite with it yet. So we're doing 2 to the x. If we put in a 0, 2 to the 0 power is 1, 2 to the first power is 2, 2 to the negative 1 would be 1/2, 2 to the second power would be 4, 2 to the third power would be 8, okay? Just putting in a bunch of values here. So we get 0, 1, which as long as A doesn't mess with it, B will, at 0, it will always be 1, okay, unless A multiplies it by something. But as long as you just have a B to the x, it will go through 0, 1. 1, 2, 2, 4, 3, 8, negative 1, 1/2. And it does get smaller and smaller. If you put in negative 2, you get 1/4. Negative 3, you get 1/8. It's just getting closer and closer. It doesn't actually ever become 0, but it can become so infinitely small that our calculator can't calculate it or doesn't know how to draw it. Okay. So this is called a growth function because b was greater than 1. It has a domain of all real numbers. It has a range. It doesn't actually touch 0. That's bottom to top, okay? The y-intercept is at 0, 1. It has an asymptote that is the x-axis, whose equation is y equals 0. Increasing is the whole thing, so negative infinity to infinity. It has no decreasing section. All right, I'm going to just use y here. The y is approaching 0 as x goes to the left. The y is approaching, I should be using f of x, but it's just more writing, infinity as x approaches infinity. So as we go off to the right, it's going up. All right, let's see. So here's 1/2 to the x, which is like 2 to the negative 1 to the x. But if we just think of it, if we put in 1/2 to what power? So if we put in a 0, 1/2 to the 0 power is 1. 1/2 to the first power is 1/2. 1/2 to the second power is 1/4. Okay, not going anywhere fast, getting tiny. But if we put in a negative 1, that flips it over. Remember, negative exponents mean everything's on the wrong side of the fraction bar. So it becomes positive 2. Negative 2 flips it over and squares it. So it would be positive 4. So 0, 1 again. But this time it's getting smaller as we go this way. And it's getting bigger as we go this way. So this one is the shape of a decay function. Domain is still all real numbers. Range is everything above 0. The y-intercept is still 0, 1. The asymptote is still the x-axis, which is the equation y equals 0. It is never increasing. It is always decreasing from left to right. And remember, it doesn't actually flatten out. It just goes down infinitely small little intervals there. And let's see, on the left side, it is approaching 0, infinity this time. It's going up. On the right side, as x approaches infinity, it is getting closer and closer to 0. All right. Now, this is an extra slide that I stuck in here to talk about the number e. It is often called Euler's number. It's pronounced like Euler. This looks like Euler or something, but it's Euler. And it is the base of the natural logarithms, which were invented by John Napier, and has lots of applications. I like the next slide here because I show you how they actually come about this. This is the definition. If you took 1 plus 1 over x all to the x power, and you, on the right-hand side, as you put in bigger and bigger and bigger numbers, what happens is this value approaches, see how it gets closer every time you put a bigger number in there, it gets closer to this magical irrational number called e, okay? E is like pi, it goes on forever, okay? And it doesn't repeat. And because it looks just like 2 to the x, okay, it's just growing by some weird 2.17 number. So e is an irrational number with an approximate value of, I'm going to go back to this slide so I can put down several places, 2.71814. No, is that right at the bottom? I didn't. No, 2.71828. Okay, we're not going to need that many places. And it is on your calculator. It's actually 2 different places on your calculator. I would highly suggest, because most of the time that we use E, you need to use the power. So I would suggest you, most of the time you use second and then ln, which is 2 above on. And that will bring up e to the, so there's our calculator's version of e to the first. but most of the time we're going to need to put a power in there, so it's easier to use that one. It is also somewhere on here is a plain old little e. I don't even remember where it is. Oh, here, it's above the divide. You can use that little e as well, but I always use second ln because we're going to use it to undo logs, etc. All right, exponential functions with base e are called natural base exponential functions. So it is f of x equals a times e to the x. Many real-world applications use base e, so we're going to graph it real quick. Basically, it's when you put in a 1, you get out an e, which remember was like 2.7. When you put in a -1, you get 1 over e. Let me do that on my calculator fast here. Oh, sorry, I had something else in my calculator, which is about 0.4. I'm just going to say 0.4 because we can't graph it with any accuracy anyway. If we put in a 0, anything to the 0 is 1. And if we put in a 2, e squared would be 7.4 approximately. All right, so it still has an intercept at 0, 1. At 1, it's almost up to 3. And at 2, let's see, 3, 4, 5, 6, 7.4. I don't know if I did that right. 1, 2, 1, 2, 3, 4, 5, 6, 7, and a little more. Okay, somewhere up there. And then going this way, it's getting smaller, just like 2 to the x. Except it goes up a little faster because it's e. So it's growth, all real numbers, 0 to infinity, y equals 0 or the x-axis, 0, 1. It is all increasing, never decreasing, and behavior on the right, on the left, is approaching 0, and it's approaching infinity on the right. Okay, I know I went really fast, but it's very much like y equals 2 to the x. All right. Now, these are about transformations of these graphs. Anything we do inside with the x, so like e to the x minus 3, sorry, let's make it plus, would be a shift left, okay? If we had a shift right, it would be like 3 times 2 to the x minus 5. Now the 3 would also be stretching it, but we'll get there. To shift it up, you add it on the back of the function. So that would be like 1/2 to the x, and then a plus 7 on the back would shift it up. All right, and if we had a 6e to the x minus 4, that would shift it down. All right, a reflection on the whole function flips it over the x-axis. That would be like -3 times 2 to the x, okay? And you don't really need those parentheses. But be real careful, that 3 times 2 is not 6 right there. The 2 is to the x, the 3 is multiplied after you do the exponent. All right, and a -x, like e to the -x, reflects it over the y-axis. And then out in front, the a is a vertical shrink or compression, or I'm sorry, stretch or compression. If it's greater than 1, it stretches it up faster. If it's less than 1, it shrinks it down. And a horizontal stretch or compression would go inside, and I don't think we'll have very many of those. All right, so what would happen here is our basic shape that looked like this, okay, is shifted up here is on the x, so that's a opposite of, so right 1, and then the plus 1 on the back of the whole thing is an up 1, so that new function would shift right 1, so instead of 0, 1, it would go right 1 to 1, 1, but then up 1, so it would be at 1, 2 up there, all right, and it would, be doing something like that. And then e to the negative x is e to the x, which looks like this, and it's reflected across on the x, so it changes x values, so it's horizontally changing across the y-axis. It's flipping left to right, so it would now look like this. It would be a decay function. All right. Here are some additional examples that you don't have. This would be left one. This would be over the y-axis. This is a reflection over x and a vertical stretch. And the order doesn't matter there. All right. So we're supposed to describe these transformations and then graph it. So y equals 3 to the x would look like this. All right. That's a minus 1, so it's shifted right 1 and down 4. So down 4 changes this horizontal asymptote here that was x equals 0 is going to be down at negative 4. So it has an asymptote at y equals negative 4. All right, and normally it went, when we put in a 0, it went through 1. So we were here, 0, 1, but that has shifted, okay, right 1 and down 4 here. But let's talk about that. Let's just put a couple values in. If we put a 0 in, we'd get 3 to the 1, which would be 3, minus 4 is going to be negative 1. If we put a, what's happening here? This should be growing. 3 to the 0. Oh, I messed up. Not the first time. Won't be the last time. Okay, so I put a 0 in. I have 3 to the negative 1 minus 4, which is 1/3 minus 4. Try to use my calculator real fast. 1/3 minus 4 is negative 3.7. So that was when I put a 0 in. All right, now I need to erase this. At 0, it's down at negative 3.7 right there. Okay, now if I put a negative 1 in, I'd have 3 to the negative 2 minus 4. I can type that in just to get a decimal for you. I get negative 3.88. It's getting closer and closer to this line as we go this way. All right, let's see what happens when I put a 2 in. Sorry, negative 1 was negative 3.9. If I put a positive 1 in, did I already do that one? We'd get 1 minus 4 is negative 3. That's the one I plotted right there, 1, negative 3. If I put a 2 in, let's do at least one more point here. We'd have 3 to the 2 minus 1 minus 4, which would be 3 minus 4 is negative 1. So at 2, it's down at negative 1. If I were to put a 3 in, I'd have, this would become 3 squared, which is 9, minus 4 is 5. 1, 2, 3, 4, 5, okay? Now, if you're thinking, let's just go to the calculator, you are absolutely fine to do that. You can just grab your calculator and go to 3 to the power of, if you have an older calculator, you need parentheses up here. Okay, if the newer ones, if it's in that little box, you really don't. And then it was minus 4. I'm going to do a standard window. Now, it is not perfectly horizontal here, but it certainly looks like it. And then you could go to the table to find some values. Okay. It is increasing. Oh, I suppose I should do all of these. You know what? Maybe I'll just skip that. I'll go back and do that on the slides. The biggie is here that it is has an asymptote at -4. It is all increasing, and the y-intercept was at 0, and when we put in a 0, it was, we rounded to -3.7. That's fine, I don't care. It is never, and the end behavior as x approaches -infinity, y is approaching -4, because that's where the asymptote went, and then it's going up on the right. All right. Let's just describe the transformations on this one. 1/2 x goes this way, and this one is reflected over, it's on the outside, so it's the x-axis, which would make it look like this, and then it's shifted up too. All right, so the x-axis is usually the asymptote. It would flip up here, it would move up here, I mean, and then the graph would be down here, and then you could do it on your calculator. I'll just put this one in the notes, okay? Extra example, again, this one is a growth function going this way, and it's shifted left 3 and down 5. So the asymptote would be down here at -5. And the left 3 means instead of 0, 1 here, it's going to go left 2, 3, and down 5. And that's going to be a nice dot here, and it's going to be doing this, okay? All right, the second part of this lesson is applications, and this is the fun stuff that you remember from last year, I hope. So starting at about minute 22 is where we hit the applications. So the formulas we need are, this is your basic exponential growth and decay, and sometimes it looks like this. You say the future amount is the present amount times 1 plus or minus some rate, depending if it's growing or decaying. They just say you could put a -r in here if it's decaying, and then it's to the time. Okay, that's just another version of the same formula. They use n sub 0 to say the initial amount. You should do that, like in your science classes, they use that notation. All right, continuous growth or decay, and it has to say the word continuous, all right, would be A equals P times E to the RT, which is usually used for compound interest, but it also works for anything that's growing exponentially. And again, you put a negative rate or K value in their formula if it's decaying, all right? And then compound interest is like I have $1,000 and it's growing 1 plus 0.05%, we'll say, but it's compounded monthly, so you put a 12 down there. So n is the number of times it's compounded each year, so that goes down here. Remember, in all of these, your rate has to be a decimal. So move it over. You know, if you had 6%, it would become 0.06. All right, back to my example here, and it's to the power of nt, so it's to the power of, if you have an older calculator, you need parentheses. I was doing monthly, so it would be 12 times, say I left it in there 5 or 6 years, you'd have 6 up there. All right, examples on the next page. So again, this is an extra slide, but in case you get confused, it does go over semi-annually is twice a year, quarterly is 4 times a year, monthly 12, daily 365. Some people use 360 for that number. My daughter's taking a business class right now and they use 360 for some reason. And hourly, which almost never use. And continuous, okay, this is just an extra slide, again, about that PERT formula, we like to call it. And these are just more information about exponential growth and decay. Is it growing at some kind of a growth rate or continuous? You have to have that word continuous to use that formula. All right, here we go. A researcher estimates the initial population of a colony of cells is 100, so that's n sub 0. If the cells reproduce at a rate of 25% per week, so R is 25% or 0.25. We get rid of the percent symbol. What is the expected population of the colony in 6 weeks? Now this is per week, so our time is just 6. So it's 100 times 1 plus 0.25, which you can just type 1.25 to the 6th. We type that in real fast. And we get 381.5, almost 0.5, 0.46. I'm just going to round to the nearest 10th, doesn't matter. All right. This one is finance. Says Lance has a bank account that will allow him to invest $1,000 at a 5% interest rate compounded continuously. That's how we know we need this PERT formula. If there are no other deposits or withdrawals, what will he have after 10 years? Okay, by the way, 5% interest is more than anybody's getting these days, let me tell you. So 1,000 initially, e to the power of r would be 0.05. And times 10 years, okay? And again, if on the newer calculators, you don't need the parentheses around the top because it puts it up in that little box, but I'm just gonna write it that way so you know it is part of the exponent. All right, I got 1648.72. Money, you always want to round to the nearest penny. Right. Find our balance after 10 years of a $5,000 investment, earning 8.5% compounded quarterly. So this is this formula. All right, lots of stuff going on here. 10 years is T. This is our initial investment. This is our rate, which is going to become 0.085. Move decimals carefully. And quarterly means n is 4. So we have 5,000, 1 plus 0.085 divided by 4, and then to the power of 4 times 10 years. All right. You don't actually need extra parentheses around this. But what you cannot type is, hang on. What you cannot do is write 1.085 divided by 4. That will not work, okay? Because this is dividing before it adds. Only the interest is divided out over 4. This would actually make your account decrease, and that would be why you knew you were in trouble. All right. I suppose I should type one on the calculator here. So it's 4,000, wasn't it? Or am I wrong already? No, it's 5,000. And then 0.085 and 4, okay. 1 plus 0.085 divided by 4 to the power of 4 times 10. As long as you have a newer calculator and it goes up in those little exponent box, then you're good. So I have $11,594.52. So we just need to round to the nearest penny. 11,594.52. All right, again, nobody's getting 8.5% interest. It used to be that way, but not for years now. All right, It is estimated that the United States in 2017 was using 200 quadrillion thermal units. I don't want to put all those zeros, so I'm just going to use the number 200, and then this is going to be my label at the end. All right, if energy consumption increases, so we're using plus 5% annually, what amount will they use in 2025? So here we need that time is the difference of those, which is 8 years. It doesn't say continuously, so we're just going to use 1 plus. Now, if R is 0.5%, when we move the decimal back twice, we get that it becomes 0.005. And it's annually, so it's not like a compounded question. And we said 8 years, and it started at 200. So 200 times 1 plus 0.005 to the 8 is about 208.14, I'm not going to worry about it, quadrillion thermal units. Okay? I think there's one more, maybe two more. Okay, the number of rabbits in a field showed an increase 10% each month over the last year. If there were 10 rabbits last year, so we have, doesn't say continuously, so it's 1 plus 0.1, 10%. How many rabbits are there now? Well, in 1 year, it did this for 12 months, so we're going to put a 12 up here. So we just have to read carefully sometimes. So I got 31.38, or about 31 rabbits. And the assignment on this is on Delta Math, so read real carefully how you're supposed to round, okay? And it's homework, so you will get a chance to fix it if you did it wrong. All right, one more. Population of a town is declining. Finally, we have one that's declining 6%. If the current population is this, so there's our n sub 0, predict the population in 10 years if we are doing this continuously versus annually, all right? So here we're using 1 minus 0.06 for 10 years, starting with 12,426 people, sorry. And over here, we're going to do 12,426 people, and it's E, didn't need that parenthesis, sorry. E to the negative 0.06. When you're doing continuously and it's decaying, or declining, you do negative rate. And then times 10 years. Okay, I hope those two formulas, you could have picked out the right one. Here you could definitely use 0.94. You could do the subtraction first. Just make sure the 10 is in the exponent. So I got that it's down to 6692.8. I'm going to say about 6693 people. And this one, with the E to the negative 0.06 times 10 is 6819.5, or about 6820 people. All right, so if it is decreasing annually versus continually, it came out two slightly different numbers, but they should be very close together. All right, I think that's it. I do have a couple extra practice things here. An extra compounded quarterly. I'll go back and do those other ones on the notes, but let's do another compound interest. $1,000, 1 plus 2 3/8. If you do 2 plus 3 divided by 8 on your calculator, you get 2.375, and then you still have to move it over twice, so it's 0.02375. You should use all the decimals. And then quarterly is 4, and 4 times a year, 4, from 1990 to 2025 would be 35 years. So we're going to type that in, 1,000 parenthesis 1 plus 0.02375 divided by 4, close parenthesis, to the power of 4 times 35 is $2,290.55 when we round to the nearest penny. All right, so that was one more compound interest. This is a multiple choice. This is a decay. So that tells me that the B value has to be less than 1. So the number in the parenthesis. So it can't be either of those. And after that, I would just go with the fact that when you put in a 0, you got out a 2. So I'm thinking this is the one I put in a 0. That would make this 1, and 2 times 1 is 2. This one, if I put a 0 in, I get out 3. So choice G. That is an SAT prep question, by the way. All right. This is writing. And again, I'll do these in the notes, but I'm going to stop at 37 minutes. I think that's plenty for a 2-part video here all in one. All right, Delta Math practice on this stuff, guys.